Welcome to Kushar Academy, Unleashing Potential. Chapter 2, Work, Energy and Power, Part 2. In this, we are going to study about different forms of energy. First of all, we are going to study about mechanical energy and its different forms. What is mechanical energy? Mechanical energy is said to be possessed by a body due to its state of rest or motion. Means, if a body is moving, then it is said to possess mechanical energy, and due to its states of rest means a body at a height or say spring, when it is compressed, when it is at a state of rest, it is also said to possess mechanical energy. Mechanical energy due to the state of motion or rest are divided into two subparts. One is known as kinetic energy and another is known as potential energy. So mechanical energy is the sum total of kinetic energy and potential energy of a body. For example, a body can be moving and it will be having some internal energy also due to its some position. So sum total is mechanical energy, and we are classifying mechanical energy into two parts, kinetic and potential energy. Now, what is kinetic energy? Let's discuss in little detail. Energy possessed by a body by virtue of its state of motion is called kinetic energy. Any moving object is having an energy because a moving object can do some work. And recall, what is work? Work is when the force is applied and a body moves in the direction of force. So here we can see in an example, a force is applied by the ball and this person has moved to a certain distance. Hence the work is done, and work is done by whom? By this moving ball. And this moving ball, since it is moving, it is said to have kinetic energy. Now, the kinetic energy possessed by a moving body can be measured. How do we measure it? How much work it has done on this person. So, it can be measured by amount of work which the moving body can perform before coming to rest. For example, suppose there is a car and it has kinetic energy. That means it is moving with some velocity v. Suppose a moving car hits a person and drags the person through a distance of s. Now the force is applied by the car, and due to this force the velocity of this person changes from, suppose he was standing still here, to 0 to v. Now this force is provided by car. What we are saying, kinetic energy possessed by a moving body can be measured by the amount of work which was moving body can perform before coming to rest. So this kinetic energy to this man was provided by the moving car. So amount of work done by moving car on this person, since the force was applied, so we can calculate the amount of work done, and displacement was also there, so we can calculate the amount of work done. So amount of work done on the person is force into displacement. So suppose the force applied on this, since the body was, suppose the body accelerated, the person accelerated by a, so force applied on the person was m into a, and recall from the kinematic equation v square equals u square plus 2as. Now since the initial velocity of the person we are taking to be 0, so s comes as v square by 2a. This s is the displacement that this person did from this point to this point. So substituting the displacement of the person and the force applied, so the work done on the person was ma into v square by 2a. Solving it, we get half mv square. So this car provided an energy of work. It did some work on the person, and this person, what was the amount of work done on this person? It was half mv square. If the complete transmission of energy is done from car to the person energy is half mv square, and person energy is due to the motion that it possesses. So we can say the kinetic energy of the person was half mv square. So K equals F into S. F is ma into v square by 2a is half mv square. So Since this energy is possessed due to motion, it is known as kinetic energy, and it is half mass into velocity square. Now, we will be seeing the relationship between kinetic energy and momentum. We have already seen in the previous slide that kinetic energy of a moving body, which is moving at the velocity of v, is given as half mv square. Since it is moving with velocity v, the momentum of the body is said to be mv, or velocity can be written as p by m. From equation 1 and 2, we can say, substituting v, equation 2, substituting v in equation 1, we get k equals half m. For v, we will be putting p by m, and again square, p square by 2m. So p square comes as 2mk, where k is the kinetic energy and p is the momentum. So taking roots on both sides, p equals root 2mk. Or kinetic energy in terms of momentum can be written as p square by 2m. Now this is a very important theorem known as work-energy theorem. What it says? It says, according to work-energy theorem, the work done by the force on a moving body is equal to the increase in its kinetic energy. Recall what we said in the first slide where we had discussed about the kinetic, how to derive the kinetic energy of a moving body. What we said, the kinetic energy was provided by some force, and due to the force, the body attained some velocity, and the amount of work done by that force was got converted entirely into the kinetic energy, and we derived that kinetic energy, or the energy possessed or increased in the body, was half mv square. It's the same thing. In that case, we had taken that the person initially was at rest. In the scenario, what we are taking, that suppose this person was moving initially with velocity u. Due to some force, like here, I am applying the force, so its velocity got increased to v. So the person's initial velocity was u. Due to some force F, this velocity got increased to v. What we are saying, that work done by the force on a moving body is equal to the increase in its kinetic energy. Suppose the force was applied till, and the person got displaced till here. Let the displacement be s. Now coming here, work done by the force, external force, is force into displacement. Suppose the force was F and the displacement was s. So it is F into s. We have from third kinematic equation, v square equals u square plus 2as. So displacement comes to v square minus u square by 2a, and force is mass into acceleration. Substituting it, we get half mv square minus half mu square. So half mv square was final kinetic energy at this position at point P, and at point A it was u. So what was the increase? There was an increase in kinetic energy, and how much was the increase in kinetic energy? Half mv square minus initial energy, which is half mu square. So k final minus k initial. So this is the increase in kinetic energy, and this increase in kinetic energy is exactly equal to the work done by the external force which was applied on this man, due to which its velocity increased from u to v. Now, mechanical energy constitutes of kinetic energy and potential energy. We are dividing kinetic energy also in subtypes, like translational kinetic energy means straight line movement of car in a straight path. Rotational kinetic energy, when something is rotating, like a spinning top, or even the planets or the moons are rotating in its axis, that is also some movement, and that special movement has kinetic energy, and it's specially named as rotational kinetic energy. Then vibrational kinetic energy, all the molecules, atoms vibrate, we know that from chemistry, and since it is vibrating, there is some motion, and due to that motion, it is also known as vibrational kinetic energy. Not all these are forms of kinetic energy only, because motion is associated with it. We are just dividing into subparts, special conditions, and we name it according to the conditions that they are moving in. Now, What is vibrational kinetic energy? For example, a pendulum. For example, a pendulum moves from point A to point B and again from point B to point A, and it keeps on moving. So it is getting repeated. This kind of to and fro movement about its mean position is known as vibrational motion. Violin string is also an example of this. Spring movement is also an example of vibrational motion. Now coming to the other part of mechanical energy. One was kinetic energy, which we have studied. Now we will be studying potential energy. So energy possessed by a body by the virtue of its specific position or changed configuration is called potential energy. Due to its position, if it is able to do some work, we say it is having. For example, here the stretched rubber string can throw a stone from this point to say this point. Since it is moving and the force is provided by this rubber spring, there is some work done, and this work done is due to the energy possessed by, not by the motion but by the position. The stretched position of the string is known as potential energy. There are different forms of potential energy. Generally, we divide into two parts. One is gravitational potential energy and another due to change in the shape or size that we call as elastic potential energy. So coming to gravitational potential energy. The potential energy possessed by a body due to its position relative to the center of the earth is called gravitational potential energy. Suppose this is the earth's surface. A body can be at here at say point A, and body can be here at the point B. So this position is different or at a different distance from the center of the earth. The potential energy is possessed by a body due to its position relative to the center of the earth. So if the position is up or down, it is said to possess potential energy. By convention, if it is at ground, at the surface of the earth, we say the potential energy is 0, and higher we go, we say the potential energy is more and more. Elastic potential energy. Potential energy possessed by a body in the deformed state due to change in its configuration. For example, here the string is elastic and we are changing or deforming it. The string was initially straight line here like this. We stretched it in this way. A deformity was created, and due to this deformity only this arrow was able to move, or the force was able to be applied on this arrow in turn, which enabled the arrow to move ahead. So it was due to this deformity that it possessed an energy. This kind of energy is said to be elastic potential energy. The gravitational potential energy of a body at a height h above the ground is measured by the amount of work done in lifting it up to the height against the force of gravity. Now let's see here. Suppose the elephant was at the ground here and somebody lifted it to the height h. So again we are able to see what is going to happen here. Suppose I am so strong that I was able to lift the elephant from ground to this position, which is at a vertical height of h. Now I had to apply some force on elephant. Suppose there was no acceleration. In that situation, how much force do I have to apply? At least what was the force of gravity? Because gravity was pulling, force of gravity was downstairs. My muscular force was upstairs, and at least I have to apply this force so that I am able to lift the elephant till this point. Suppose the ground point is A and the point above h height is B, where I have put the elephant. So I am applying the force F. Now what was the force of gravity? The force of gravity was mg. So I am applying at least mg force on elephant in order to put it here. Now what was the work done by me? It was force that I have applied and the height that I, or the distance that I have moved. How much distance I have moved? I have moved h distance. So work done by me on lifting the elephant till height h is F into h. So the work done by me in lifting elephant from this point to this point is the force that I have applied. At least I have to apply gravitational force F, that is mg, and how much the distance I have traveled due to this applying this force, it was h. So work done is F into h, and F is mg. So substituting for force it is mg, and for height it is h, which is mgh. So mgh. So this was the work done by me on the elephant. So I have lost energy and elephant has gained energy. And how much elephant has gained energy? It was the work that I had done on elephant, and the work that I had done on elephant was mgh. And this is due to the position. So we say that the gravitational potential energy at a height h is mgh. A conversion of potential energy to kinetic energy. We know that energy can neither be created nor be destroyed, but can be converted from one form to another form. Potential energy changes into kinetic energy whenever it is to use. For example, if I am stretching the string, it is having potential energy, and if I am releasing the string, the potential energy stored in the string gives a kinetic energy to the pellet, and pellet moves at a velocity. Here also, suppose this is the mean position, it is moving at a height here, so it has stopped completely here, so it is having only potential energy at this point. Similarly, at this point it is having only potential energy, and in between it is having potential energy as well as kinetic energy. Note at the central point the kinetic energy is highest. Examples, we'll study about some examples of conversion of potential energy to kinetic energy. One example is ball falling from a height. A ball at a height h above the ground is having an potential energy, and how much potential energy it is having? It is having mgh. We had already seen how we had derived mgh, and when here the velocity is 0, at this point it is having potential energy. How much potential energy? Suppose this is x height, so the potential energy at a point A will be given by mgx. Now rest of the potential energy, what is the difference of the potential energy that it lost? It is mgh minus mgx. This is the potential energy that we lost, and this potential energy got converted into the kinetic energy of the ball if the velocity of the ball here is v, so half mv square. So at point A we can find the velocity of a ball by conservation of energy also, because here the total energy was mgh, here the total energy will be mgx plus half mv square. If we put this mgx on this side, we get mgh equals to mgx plus half mv square. First example was due to the gravitational potential energy. Second is due to the position. A wound up watch spring. In the earlier days, the wristwatch used to have a spring, and we used to rotate it every morning, and this rotation used to recoil the spring, and the spring slowly used to move the second hand and hour's hand. It was due to the energy stored in the spring due to winding of the spring, and it got converted to the kinetic energy of the second and minute hands. Third example, bow and arrow. This bow is stretched, the string is deformed, it is having potential energy, and this potential energy gets transferred to the kinetic energy of the arrow, and it loses its potential energy. Compressed spring, if we put a ball and compress it, when we release it, the ball gains a kinetic energy, and the potential energy of the spring reduces or comes to 0 when the spring is at its free state.